Our next speaker, as you know, is Professor Alex Lubotzky from the Hebrew University, who is also now associated with the Weizmann Institute in Israel. He has visited India quite a few times and familiar with Indian context and all that. And and now today he's going to speak to us on the topic for you, uniform stability of high rank lattices. Over to you, Alex.
Thank you very much, Danny, and I'm so sorry that I cannot be with you and all my friends in India. As you know, I love to visit India. I take every opportunity to do that. Unfortunately, the war in Israel did not enable me to come. I cannot. I mean, this is not the worst outcome of the war, but still, I feel pity for that. What I'll talk today, as you say, is about uniform stability of high-rank lattices, and this is a joint work with Lev Glebsky and Nicola Monod and w.r.t. Rangarajan from India, who is a student of mine, is really a lovely person and a great guy and wonderful mathematician. And I'm very proud to talk in India on a joint work with an Indian person. So let me first explain what is the title about. What is stability? This is a kind of not so new, but there is a recent interest in this type of rigidity. What is usually a typical rigidity results in this audience? I don't think I have to explain that, but just to put it in line of the other remarkable rigidity results, usually in rigidity we say, well, we have a clear representation. Let's say that every lattice in a semi-simple group has those representation coming from the semi-simple group, and the finite representation, and basically say super-rigidity tells you that all representations are kind of combination of these clear combination of the clear families of representation. What I'll talk today is uniform stability. Sometimes it's called Ulam stability, because Ulam was maybe the first one to ask about this type of questions. And sometimes when we don't know whether we want to call it Ulam stability or uniform stability, we simply call it U stability. And when we use the letter U stability, then you can understand it either as Ulam stability or uniform stability, which are really the same. Okay, but before I want to a warning. Don't confuse it with the ordinary stability. There are two notions of stability. Both of them are very, very interesting. Both of them are useful for many things. Both of them deals with the issue of we have a almost representation, something which is vaguely representation. Is it nearby a true representation? So let me for a minute give the precise definition. The ordinary stability can be expressed. There are various ways to express it, but because now I want to compare it with uniform stability, I will express it this way. Let phi n from gamma to gn be maps, not, I stress, not homomorphism. These are just maps from the group gamma to a family of groups Gn, to one of the family, phi n is from gamma to Gn, such that for every you fix Gnh in gamma, then the distance between phi n of gh and phi n g, phi n h goes to 0 when n goes to infinity. So you have a sequence of maps. that eventually they behave like homomorphism, but this is locally. For every G and H, it goes to 0. Then we say that gamma is stable with respect to the family Gn if whenever we have such maps, there are true homomorphism, psi-n, from gamma to Gn, such that the distance between, for every G, the distance between phi-n of G and psi-n of G goes to 0, again goes to 0 for every G in gamma. This is the ordinary stability, which was studied quite a lot in, it's an old subject, but somewhere in the last decade, there is a lot of interest in that. And now we will go to the talk of today, which will be about uniform stability. It starts similarly. We have a family of phi-n of gamma to Gn, such that the supremum over all G and H of the distance between phi-n, here it should be phi-n of G times H, just like here, I'm sorry, this is a typo, phi-n of G times H and phi-n G, phi-n H goes to 0. So it goes to 0 in a stronger way than in the ordinary stability, like it goes, all of them together with the same rate goes to 0. Then we want a stronger conclusion. Then there exists psi-n from gamma to n, such that again the supremum between phi-n of the distance between phi-n of G and psi-n of G goes to 0. Again in a uniform rate. Now, I want to stress that it's possible that group will be ordinary stable without being uniform stable, and the opposite. For example, kind of is not so easy exercise. The easy exercise is to say that every free group is ordinary stable, but the free group are not uniform stable. That's less trivial. But this is a good hint for us that the free group are not uniform stable, because we'll continue with this. Sorry. So the free group are not uniform stable. Okay, now today, what we are going to do, we are working only with one family, which is of great interest, and the Gn are the unitary groups, Un, and Dn is the metric induced by some multiplicative norm. You can take if you have such a norm, sub-multiplicative norm, it means that the norm of AB is less or equal the norm of A times the norm of B, and we define the distance between A and B to be simply the norm of A minus B. So the example include the operator norm, the Frobenius norm, which is simply the L2 norm, the so-called P-Schachten norm for every P between 1 and infinity, when this time the norm is the P norm, the P-Schachten norm, trace of A to the P, we take A absolute value, which is simply the square root of A, again, this is a typo, not A times A, but a joint term A. If you take the joint of A times A, this is a non-negative matrix. It's a normal operator. It can be diagonalized. All eigenvalues are real and non-negative, so we can take square root. So this is the absolute value of A. We take the trace of A to the P, and then 1 over P. If you think about it for a second, you see that for P equal 2, this is just the ordinary L2 norms. And this is also a sub-multiplicative norm. I want to stress that there are norms which are not sub-multiplicative, and our results does not apply to them. For example, the Hilbert-Schmidt. The Hilbert-Schmidt norm is basically nothing more than the Frobenius norm, the L2 norm, but normalized. You divide it by 1 over square root of n. And it's kind of amazing in this theory that usually, I mean, in our theorem, we include all these sub-multiplicative norm, but usually you may prove stability to one norm and it says nothing on a different norm. I will leave you to think about it, because even if you know, for example, if you know that the Hilbert-Schmidt norm is always less than the Frobenius norm, which means that if you go back to the definition, what did I do? Oh, yeah, if you go back to the definition, then you can see that what did I do? Oh my God. I jump over. Okay, I'll go back to that. I jump over some slides. What did I do? Oh. Anyway, you can see that sometimes you have a challenge, which is you have phi n, which are a challenge to the stability in one norm. If you go to a smaller norm, this is clearly a challenge for the smaller norm. But the fact that you can solve it with the Frobenius norm, with the bigger norm, does not mean that you can solve it with the smaller norm. Okay, that's something trivial, but sometimes it's a bit confusing. Anyway, it seems that I made a mistake.
Alex, your slides are not moving.
I made a mistake and I jump over. Yeah, I made a mistake and I jump over slides, so that's okay. I will go back to the first slide. Doesn't matter. I mean, this warning had to be said after the theorem was said. So let me go. Let me start again, but that's okay. Let G be a I talked today about simple because from technical reason you can deduce to semi-simple from the simple, but I don't want to be bothered by that. Let G be a simple Lie group over some local field, and gamma a lattice. So in this audience, we all know we talk about uniform, compact lattices, a non-uniform. The rank of G will be always the rank of G over the local field K. Now, we know, like we have experience in rigidity, we know that usually the difference is between rank 1 and I rank, but not always. For example, super-rigidity holds for all I rank, but also for some rank 1. Strong rigidity also applies to most of rank 1. Local rigidity, the same. So there is kind of it's a typical distinction between I rank and rank 1. Like if you want SL2Z versus SLNZ and greater equal T, but not always. In our case, yeah, I'm sorry that I saw all this and the jump. Okay. Yeah. So now I will redefine uniform stability, which is equivalent to what I said before. I'm sorry that I jumped. Let gamma be a group and Gn, Dn a family of groups such that Dn are bi-invariant matrix. So gamma is uniform or Ulam stable. You see that will be exactly the same definition what I mentioned before, but it's just expressed by epsilon delta language. If for every epsilon there exists delta, such that for every n and for every single map from gamma to Gn, which satisfy that the distance between phi of GH to phi g, phi h is less than delta, so these are almost homomorphism. Assume this happens for every g and h, so this is in a uniform way. Then there exists an homomorphism from gamma to gn, which is a true homomorphism whose distance from phi is uniformly less than epsilon. So which means that this Ulam stability means that every almost homomorphism in this sense, in the uniform sense, is uniformly close to a true homomorphism. And then I said, what I mentioned before, do not confuse it with the ordinary stability. In the ordinary stability is what I already told you, is that if we have phi n, so that they are it's homomorphism which are locally looks like almost homomorphism, there are true homomorphism which are locally close to that. In the Ulam stability, we work so that the supremum goes to 0. Okay, I said it too many times. So now I say that today we will work only with Gn are the unitary group, and we assume all the time that the metric is sub-multiplicative. It looks like a technical condition, but I want to stress that in general, we don't know what is the answer to the type of question that I will talk about today for the Hilbert-Schmidt. We are using it in a substantial way that the norm is sub-multiplicative. And now, sorry, after all this confusion, I can give you the main result. The main result is the following. If we are working, that's again a joint work with Lev Glebsky and Nicola Monad and w.r.t Rangarajan. And if G is the family of groups UN, Dn, where Dn is a sub-multiplicative, I mean, it's a matrix coming from a sub-multiplicative norm. If gamma a lattice in a high-rank simple Lie group, namely a Lie group of over local field of rank greater or equal to 2, then G is Ulam stable, provided it satisfies some technical condition that I will define later, GQ1, GQ2. Unfortunately, we cannot prove it in the complete generality, and it's a nice, good challenge to try to complete our theorem. It's almost complete. I will define it later because it's kind of technical. I just tell you now that the condition is automatically satisfied for most simple groups. For example, if G is a is a Lie group over the complex number, then it's automatically satisfied. If K is a non-Archimedean field, it's automatically satisfied. The only problem is if K equal R, then some groups satisfy it. For example, SLDR satisfies it for D greater or equal 4, but SL3R does not. And SP2GR, none of them satisfy it. So, but many other Lie groups do satisfy them. So the theorem is unfortunately not yet complete, but somehow we were not able to overcome this technical difficulty, but we believe that the result is true for all high-rank lattices. Let me tell you something about the history of this problem. The first results on this type of Ulam stability is due to Kazhdan already in 1982. He proved that amenable groups are strongly Ulam stable with respect to the operator norm. Let me say, what does it mean strongly Ulam stable? Means that this is true if you take not only maps to UN, which are the finite dimension, which are the unitary operator of finite dimensional Hilbert spaces, but it's even true with respect to infinite dimensional Hilbert space. Namely, if you have a map from an amenable group to the unitary operator of some Hilbert space, which is almost homomorphism in the sense, in the strong sense, in the strong of uniform stability, then you can, then it must be a small deformation of a true homomorphism. This is a well-known basic results of Kazhdan, already in the 80s. But Burger, Ozawa, and Thom in 2013 showed that you cannot expect to extend it to non-amenable group. Maybe to some, but certainly not for general, because they prove that if any discrete group contains a free non-amenable subgroup, then gamma is not strongly Ulam stable. What is their proof? The proof says free groups are not Ulam stable. I told you that before. This was proved before them. And then they said, okay, you take a unit, you take kind of a sequence of a finite dimensional unitary representation of the free group, which are finite dimensional almost representation, which you cannot approximate them by representation, and you induce them up to get almost representation of such gamma, but these free groups are of infinite index, so these are infinite dimensional unitary representation, and you can kind of, just like in the same philosophy or a method of Kazhdan property T, that if you induce from a subgroup to a group, then you get almost representations of gamma on infinite dimensional Hilbert spaces, which cannot be approximated by true homomorphism. Now, we all know that there used to be a famous open problem that eventually was solved in a negative, that non-amenable groups always contain a free group. This is not true. So theorem 1 and theorem 2 here do not give us the complete picture. And the open problem is, does strong Ulam stability maybe this is a characterization of amenability. We don't know any non-amenable group which has the strong Ulam stable. You see, I want to stress what we proved. What we prove is the best that one can do. Not maybe the best, but we prove that these high-rank lattices are Ulam stable, not strong Ulam stable. Namely, they are Ulam stable with respect to finite dimensional Hilbert spaces, but they are not for infinite dimensional. Okay. Burger, Ozawa, and Thom, the same paper, prove also the following, and this is an hint on the connection between our subject and the bounded cohomology. They prove that if the map from H2 of the bounded cohomology of gamma with coefficients in R, if this map to H2 of gamma R is not injective, then gamma does not have Ulam stability. Now, this is known. It's known that all lattices, I stress, all lattices in rank 1 simple Lie group, that this map is not injective. This was proved by several people in different ways. Some passages I don't want to go. I think Fujirava as the most general result, but it's known that all lattices, I don't think it was known when they wrote the paper in 2013, but now it's known that this map for rank one league, for lattices in rank one groups is never injective. In fact, the left-hand side is always infinite dimensional, and H2 gamma R is always finite dimensional. So this is never injective, and therefore lattices in rank one are never Ulam stable. Now, Burger-Ozawa-Thom gave the first hint that the situation in higher rank can be different. They proved that SLDZ, or even more generally, SLDOS, or ring of integers localized at a finite set of primes, that those are Ulam stable for D greater or equal 3. But their proof cannot be generalized to all lattices in higher rank. Why? Because they use very heavily, in fact, it's not a difficult proof once you use the fact that these groups are the so-called bounded generated, namely, as a group, as a set is a direct product of finitely many cyclic groups, or in this case, in the more general case, of finitely many kind of unipotent unipotent subgroups, and you can deduce it by this bounded generation. It's a very nice proof, but not very difficult. Now, the situation about bounded generation, when they wrote the paper, maybe they could hope that their proof will be generalized to all higher rank lattices, because at that time the situation was that it was known that many of the non-uniform lattices are bounded generation. And at least some people, even many people, me included, thought or hoped that the compact lattices are also bounded generation. This could be wonderful, because bounded generation, Rapinchuk and I independently show that this implies the congruent subgroup property. So somehow we have an interest to believe that all lattices are bounded generation, and this will solve the congruent subgroup property. But life are not as good as we want, and in fact, Vaja, Rapinchuk, Ben and Zanier proved that it was kind of a big breakthrough and a surprise to all of us, I think even for Rapinchuk himself. They proved 2-3 years ago that none of the compact lattices of the uniform lattices is bounded generated. So there is no way to take the proof on Burger-Ozawa and extend it to general high-rank lattices. Okay, so we have to go to a different method. Now, but I want to say something that already the results we saw so far give some an hint on connection between our subject and the topic of bounded cohomology, namely, it's a well-known result that if gamma is an amenable group, then the bounded cohomology vanish for every n. Now, it's also known that the bounded cohomology vanish for high-rank lattices for every module V, provided V has no fixed point. Now, this was proved by Burger and Monod for n equal 2, and by Burger and Shalom, also for n equal 2, but more general V, but with a different proof. I mention it because that will be important for us soon. And Monod eventually prove it by, again, a very different proof, this time for all n. Now, this led Monod already in his ICM talk at 2000 to ask, is there a connection between Ulam stability, not with bounded generation, but with bounded cohomology? The answer is, well, yes, but there is some connection, but it's not as simple as as maybe we would wish. Now, what we did, we had in a way, this question or the work of Kazhdan and all this Burger and Ozawa-Thom was the starting point of us. We wanted to do why. So let me say something. I warn you that we are talking today about uniform stability. Still, let me say few words about ordinary stability. There has been a lot of progress on ordinary stability in recent years, and it was turned out that the second cohomology played a role there. So I will have to use the language of ultrafilters, and so let's fix, say, ultrafilter U on N. Let Ln be the Lie group of Un with the norms as before, sub-multiplicative, and let L be the ultra product of these Lie algebras. The topological ultra product, what does it mean? That we have a norm on these Lie algebras. So we say that usually in the standard ultra product, we define the two sequences are the same if they are equal on almost everywhere, like in most of the entries, most with respect to the ultrafilter. Here we want to say that topological ultrafilter, we identify two such sequences if the distance between them goes to 0 on most coordinates. To say it precisely, for every epsilon, the two are the distance between them are less than epsilon almost everywhere. Okay, if you are not so comfortable with this language, just think of it as sequences so that the distance between the sequences converge to 0. Now, if you start with almost homomorphisms, phi n, as we talked before in the standard sense, not in the unitary in the uniform sense. If you think about it for a second, you see that each one of phi n is almost homomorphism, and therefore it defines an almost homomorphism on Ln, on the Lie algebra. But when you take this ultra product and think of it, and think of this diagonal map as a diagonal action on this ultra product, then this is a true homomorphism. So somehow this nonsense of model theory logic enable us to pass from the category of almost homomorphism to the ordinary category of homomorphism, which we feel much more comfortable with. Now, if H2 of gamma, so what we proved at that time, the Schiffer, Glebsky, Thom, and me, we proved that if H2, if the second cohomology in this ultra product vanish, then you have stability, then phi n are close to homomorphisms psi n. So somehow we prove a criterion for ordinary stability. And in particular, we apply it for Venus norm, for various groups, etc., etc. But this is not my topic today. The only thing I do want to explain, because this is relevant for today's talk, is why H2. Usually, when I used to give talk about this previous work, suddenly it looks like a magic. Why H2 suddenly comes into the game? So this looks surprising, but actually we were led to that somehow naturally. Why? Because look, assume you have phi n just maps between gamma to un, right? The maps which are almost homomorphism. If you look at that, then this gamma give you a diagonal map to the direct product of un, but this map is not homomorphism. It's just diagonal map of almost homomorphisms. But if you take the topological ultra product, namely you divide this group by all the infinitesimal, by all the sequences which converge to zero, then this is a true homomorphism. So as I said before, this is a trick to go back to the category of homomorphism from the category of almost homomorphism. From infinitely many almost homomorphism, you get a unique homomorphism to this huge group. Now, this huge group is the quotient of the direct product. And if you think about it for a second, you see that gamma is stable if and only if this phi star, which is now an homomorphism to this crazy group, can be lifted to a true homomorphism to gamma to the direct product. To start with, the phi n are not homomorphism. But now if you can lift phi star to psi to a true homomorphism to the product, what does it mean? It means that for every n, you have a true homomorphism to the n coordinate, which is nearby, modulo infinitesimal, is nearby to the original phi n. So we are just in an ordinary lifting problem that we have a lot of experience in group theory with this type of problems. So somehow this little trick enable you to go back from the complicated category of almost representation to the ordinary category of representations, homomorphism and lifting problem. But there is no free lunch in this world. Because what is the problem with this cohomology, with this extension problem? That usually we know to solve this problem with an abelian kernel. We have technique for that, but in this case, K is very non-commutative group. If you think about it, it's like if you take the direct product of all the unitary group defined by these infinitesimal elements, it's really a crazy group. It's not a closed subgroup, and it's very non-commutative. Okay, the trick is that if the norm is sub-multiplicative, then you can approximate it by abelian steps. Small abelian steps, you approximate this each time slowly by better and better approximation. Similar to the story with congruent subgroups, that like the congruent subgroup mod P in arithmetic group is very non-abelian, but the congruent subgroup mod P modulo the congruent subgroup mod P square is abelian. And P square is abelian modulo P cube. And kind of you imitate this and then you solve it if the norm is abelian. So this was the main idea of the previous paper. Now, the original idea, the kind of way we started our work was to go over this, and then if you really go, I don't have time to show you the detail, but this is elementary, like to see that the cohomology, the relevant cohomology now is the bounded cohomology. So great. That's what Nicolas Monod expected in his IC. I mean, he expected this before we did our work. He just observed it that there is some connection between results. But we said, we have a solution. But, well, this is not as easy as you think, because the bounded cohomology is relevant, but you can translate it, etc. But what you have to do in order to lift it, you have, I don't have time to define it, you have to solve it using the so-called internal maps. In the now, in the ordinary stability, all this issue does not come up because the values of psi are really important only for the generators, and therefore everything is internal. I don't have time to really to tell that. Anyway, I see that times is really running. I just say that if you kind of check this, then what we get is that the group gamma is Ulam G stable if and only if every homomorphism phi that has an internal leaf as a map also has internal lift as homomorphism. Okay, I don't have time really to explain it. That's because this is really getting a fairly complicated story. Our paper is 80 pages because of this point, because this enforces us to define a new cohomology theory. We have now a new cohomology theory, which we call it the asymptotic cohomology, not the bounded cohomology. It's a kind of a bounded cohomology which was tailored in order to solve this problem. We denote it HNA of gamma with coefficients in this Lie algebra. It's really, in some sense, not just defined on gamma, it's really defined on the ultra power of gamma, but it works with internal cochain, internal cocycle, internal co-boundaries, but this is the right cohomology language to work with this uniform stability. So this is what we proved. Again, that's the work with Glebsky, Monod, and oh, I wrote Ramanujan. I meant, this is a Freudian mistake. I meant Rangarajan, my student. He's actually w.r.t. Rangarajan is from Madras, from Chennai, from the same city of Ramanujan. So I sometimes think about him as my little Ramanujan. Well, he's extremely good. Maybe not as Ramanujan, and I'm not as good as R.D., but I feel privileged to have him as a student. Not Ramanujan, Rangarajan, w.r.t. Okay. So our theorem, sorry for this typo, if H2A, if the asymptotic cohomology vanish with respect to blah, 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 what I defined before, then we have this uniform stability. I just want to mention that there is a canonical map from the asymptotic cohomology to the bounded cohomology, something similar to what is studied a lot about the map from the bounded cohomology to the ordinary cohomology, but we have no idea, we don't know to prove it. Looks, this is a new cohomology. We just defined it quite recently, and we hope that it will raise some interest and people will be able to tell us more. If this can be proved to be injective, then our work will be much easier, and that will solve the problem for all I-rank lattices, but we don't know to prove it. We can prove results like Kazhdan, that the asymptotic cohomology vanish to all amenable groups, so we recover Kazhdan theorem in this way. Okay, okay, I don't have much time, so I just say something. What we have to prove? We have to prove that the asymptotic, that's what now the goal. So the goal is to prove for our new cohomology the results which was proved by Burger, Monod, Shalom, and Monod only for dimension 2. This is difficult enough to prove that H2, the second asymptotic cohomology with coefficients in that Lie algebra, which is more precisely the topological ultra limit of the Lie algebra, that this cohomology vanished for I-rank lattice. Okay, well, our proof more or less tries to follow the proof of Monod and Shalom. I told you there are three proofs. The one which was more suitable for us to imitate was the proof of Monod and Shalom about the vanishing of H2 for these I-rank lattices of the bounded cohomology. B here instead of A. Okay, what is the first step? The first step, as you can expect, is a kind of a Shapiro lemma about induction, right? You know, what they prove. This is a standard result. If you have an I-rank, gamma is an I-rank lattice, then for every dual Banach space V with a gamma action, if you induce the module from gamma to G to the Lie group, the cohomology is the same for the bounded cohomology. This is a standard result for usually for ordinary cohomology. Well, we have to be careful. Even for ordinary cohomology is kind of a standard for co-compact lattices. Is not exactly the case for non-uniform lattices. The Shapiro lemma does not work as it is. There is actually, I should call your attention, there is a great paper by Uri Bader and Roman Sauer, which just came up a few weeks ago, where they kind of resolved this issue for non-uniform lattices by passing through. They also invented a new cohomology theory, which polynomial growth cohomology for non-uniform lattices. Anyway, this is not our subject, but I want to say that it's the same philosophy. Sometimes, if you have a problem, and we do have a problem, in our case, even to prove such a standard Shapiro induction, if you do with a different cohomology, it took us a lot of work to prove, and we eventually proved it. We proved that we have a Shapiro lemma. We have to take Ekman approach to that, and we could prove it. Why? Where we are? Oh, sorry, what happened to me? Yeah, why a lot of work? Because the problem is that we really have to work not with gamma. We have to work with the ultra product of gamma, which is, we want to think about it as a lattice in the ultra product of G, but the ultra product of G is not locally compact, right? So, and now what does it mean, for example, L infinity of G star over gamma star? What does it mean L2 of G star over gamma star? We don't have R measure. It's kind of an ultra product of the R measure of every G. So what we mean, we have to give him a meaning to each one of these notions, L infinity and L2, and we have to be careful to do it in the right way. We try various ways that will be suitable, and when you make it in the right way, then you can do it. So even such a standard Shapiro induction, and even for co-compact lattices is an issue here. Okay, so but we did it. Now we wanted to make a reduction to the trivial module. You see what happened, as I told you, we try to follow the Monod-Shalom proof. In the Monod-Shalom proof for the bounded cohomology, what they proved that if you have a separable Banach spaces with G action, then the bounded B cohomology of W is the same as the bounded cohomology of the fixed point of G, namely, it vanishes if there are no fixed points. If there are no fixed point, oh, I'm sorry, again a tip. What did I do? Oh, sorry. For a dual sep. No. Okay, sorry. Now we work with G. Sorry, we forgot about gamma. We don't have to work with gamma anymore because we reduce by the Shapiro lemma. We reduce it to G. We forget about gamma from now on. Also, if you remember, even in the theorem, eventually, I told you that the theorem is true for gamma if G satisfies something. This strange condition GQ1, Q2, namely, when we know to prove the theorem, we know to prove it for all the lattices in G, even though for every lattice is a completely different problem. In principle, it could it could happen that some lattices are Ulam stable and some are not. Okay, so we are working only, we have a module W for G. Now, what they prove that with the bounded cohomology, everything reduced to the trivial module. So if the trivial module is, if there are no fixed point, then it vanish. Well, eventually we could prove it, but now we are getting to some issues. What does it mean, a fixed point? When you see what we have, we really have that what is acting is not G, it acts, G is sitting kind of diagonally in the ultra power of it. And we and this W is an ultra. I have an hour, right? I don't have to finish yet. Somebody said something?
No, please go ahead.
Okay. So the similar. So eventually we could prove it under the condition that W has no fixed point up to infinitesimal. So we have this, but again, there is an issue which comes here. That's exactly what I said, that everything is more complicated. Okay, now we have to deal with the fixed point. And because of that fixed point, we have to introduce this strange condition. Unfortunately, we really try to overcome it, but we couldn't. To do it for all G, we could do it only under this strange condition. We somehow involve bounded cohomology. I mean, it's really a long story that I will not have in the 3 minutes that I still have. I will not be able to get to the technical details. Let me tell you just what is this strange condition GQ1, Q2. GQ1, Q2 means that G has two proper parabolic subgroups, Q1 and Q2, satisfying the following condition. Q1 intersection Q2 contains a minimal parabolic P. That's easy to arrange, right? So just take a minimal parabolic, we take Q1, Q2, and we assume that together Q1 and Q2 generate G. But now we have two conditions on the Q1 and Q2 that we need, and we need them on the bounded cohomology of this Qi with trivial coefficients. We need that H2 of B, the bounded cohomology of Qi with coefficients in R is 0. Now you can understand why we have problem, for example, with SL3. Because if you take such two parabolic groups in SL3 R, and you take the maximum, you take two maximal parabolic, they look like an amenable subgroup extended by SL2R. The amenable is not a problem. The amenable vanish. So it's a question about the bounded cohomology of SL2R. And the bounded cohomology of SL2R does not vanish. And also the same with SP. Why SP was complicated for us? Just because of this kind of technicalities. That if you take with SP, you take some kind of maximal parabolic, then well, you are getting, say, SPN -1 over amenable, and we know that SPN -1 is a central extension. The ordinary H2 is not 0, and also the non-standard is. The bounded does not vanish. But we need also, even worse, we need also that H3 either vanish or it's enough that it is Hausdorff. Now, there is actually some progress about this issue. There are some people who working on that. They had their own motivations, but some, I think, our work gave them some extra motivation to try to prove that, for semi-simple group, it's always Hausdorff. So maybe eventually this will be solved. But anyway, somehow, because of, I can say that this is not our fault that we cannot finish the theory. What we need now, we need help from the bounded cohomology people to prove for us this type of results. And then our theorem will be complete. But as I said, luckily, for most simple group, this can be proved. And our results, as of now, is quite general, but still not complete. And that's exactly now my time to finish. So thank you very much. Even though I'm frustrated that I don't see you, I thank you for listening and for allowing me to give this talk by Zoom. Thank you very much.
Thank you.